Welcome to Java Internals Interview Crashcasts, your go-to podcast for acing those tricky Java backend engineer interviews. I'm your host, Sheila, and today we're joined by Victor, a seasoned Java developer, to tackle a common interview question about Java memory management. Victor, are you ready to dive in?
Absolutely, Sheila. I'm excited to share my knowledge and hopefully help our listeners prepare for their interviews.
Great! Let's start with our question for today. Victor, can you describe the difference between the stack and the heap in Java memory?
Certainly, Sheila. At a high level, the stack and heap are two distinct areas of memory used by Java programs. The stack is used for storing method invocations and local variables, while the heap is used for storing objects and class instances.
That's a good starting point, Victor. Can you elaborate on how these two memory areas work?
Of course, the stack operates in a last-in-first-out manner, or LIFO for short. This means the last item added is the first one removed, like a stack of plates. When a method is called, a new frame is pushed onto the stack, containing local variables and partial results. When the method completes, its frame is popped off the stack. The heap, on the other hand, is used for dynamic memory allocation. Objects created with the new keyword are allocated on the heap, and their references can be stored in stack variables.
Interesting. So how does Java decide what goes on the stack versus the heap?
Great question. Generally, primitive data types and local variables are stored on the stack, while objects and their instance variables are stored on the heap. However, there's an important exception. Object references themselves are stored on the stack, but the actual object data is on the heap.
That makes sense. Now let's dive a bit deeper. Can you explain the lifecycle differences between stack and heap memory?
Certainly, stack memory is automatically allocated and deallocated as methods are called and return. It's very efficient but has a limited size. Heap memory, however, is managed by the garbage collector. Objects on the heap persist until there are no more references to them, at which point they become eligible for garbage collection.
Excellent explanation. Now let's consider some edge cases. What happens if we have a very deeply nested method call structure? How might this affect stack memory?
That's a great point to bring up, Sheila. In cases of deep recursion or many nested method calls, we can run into a stack overflow error. This occurs when the stack space is exhausted. It's important to be mindful of this when designing recursive algorithms or working with deeply nested calls.
And what about the heap? Are there any similar concerns?
Yes, absolutely. While the heap is generally larger than the stack, it's not infinite. If we create too many objects without allowing them to be garbage collected, we can run into an out-of-memory error. This can happen in scenarios like memory leaks or when working with very large datasets.
Those are important considerations. Let's talk about performance. How do the stack and heap differ in terms of memory allocation speed and overall performance impact?
That's a crucial aspect, Sheila. Stack allocation is generally faster than heap allocation because it's a simple pointer increment. Heap allocation is more complex, involving finding free memory blocks and potentially triggering garbage collection. This is why creating objects is typically more expensive than working with primitives on the stack.
Given these performance implications, are there any best practices developers should keep in mind?
Absolutely. It's generally a good idea to use primitive types when possible, especially in performance-critical code. For objects, consider object pooling for frequently created and discarded objects. Also, be mindful of creating unnecessary objects, especially in loops. Lastly, understand the concept of escape analysis, where the JVM can sometimes allocate objects on the stack if they don't escape the method scope, optimizing performance.
Thank you, Victor, for that comprehensive explanation. To wrap up, what are some common pitfalls or misconceptions about the stack and heap that interviewees should be aware of?
Great question. One common misconception is that all objects are always allocated on the heap. With modern JVM optimizations like escape analysis, some objects can be allocated on the stack. Another pitfall is assuming that stack memory is always faster. While generally true, the reality can be more nuanced due to CPU caching and JVM optimizations. Lastly, it's crucial to understand that while we can control when objects become eligible for garbage collection, we can't directly control when garbage collection occurs.
Excellent points, Victor. For our listeners preparing for interviews, remember to start with the basics of stack and heap, then be prepared to discuss more advanced topics like performance implications, edge cases, and JVM optimizations. Practice explaining these concepts clearly and concisely, and don't forget to mention real-world applications and best practices. Thank you, Victor, for sharing your expertise with us today.
It's been my pleasure, Sheila. I hope this helps our listeners in their interview preparation.
And that wraps up today's episode of Java Internals Interview Crashcasts. Join us next time for more in-depth discussions on Java backend engineering concepts. Until then, happy coding and good luck with your interviews.